Hello, and welcome to Sleepy Science by NaemVita. Whether you're listening at the end of a long day or simply letting your thoughts slow down, this is a place where curiosity unfolds gently. There's nothing you need to solve, nothing you need to remember, and nothing you need to focus on. If you notice your attention drifting, that's perfectly fine. Here, we explore one quiet idea at a time, slowly and softly. Let the words become a calm background, and let your body settle into rest. Allow your breathing to soften, slow down, and become quiet, steady, and easy. I'm glad you're here. And so we begin to drift outward, away from the familiar sounds of the room around you, away from the small concerns of the day, and gently, slowly, into something much older and much quieter than any of those things. Tonight, we are traveling, not quickly, not urgently, simply floating in the direction of the nearest star system to our own, a place called Alpha Centauri, a name that has been spoken by astronomers and sailors and dreamers for a very long time, though the stars themselves have been shining steadily and patiently for far longer than any human voice has existed to name them. There is no need to hold on to anything right now. The stars will still be there when you wake. And this story, like all good stories told in the dark, will move at the pace of your breathing. Alpha Centauri is not a single star. This is one of the first things to understand, and it is a gentle surprise, the kind that settles softly rather than startling. What we call Alpha Centauri is actually a system, a small family of stars bound together by gravity, moving through space in a slow, ancient embrace. For most of human history, people looked up at this point of light and saw only one thing: a single bright dot near the southern horizon, one of the brightest in the night sky, steady and warm in its appearance, sitting near the constellation known as Centaurus. And from Earth, it looked simple. It looked singular. It looked like a single candle flame seen from a great distance. But it was always more than that. It was always a quiet complexity wearing the disguise of simplicity. This is something the universe does often, and there is something restful in knowing that. Things appear simple at first glance, and only slowly, over time, with careful and patient attention, do they reveal their deeper nature. There is no rush in that kind of knowing. The system we now call Alpha Centauri contains 3 stars. 2 of them, named Alpha Centauri A and Alpha Centauri B, orbit each other in an elliptical dance that takes roughly 80 years to complete. 80 years, a full human lifetime spent circling. From a distance, these 2 stars appear as one because they are so close together relative to the vast distances of space, and because human eyes, even sharp and practiced ones, have their limits. The 3rd star in this family is smaller and dimmer, a red dwarf that sits much farther from the other 2, loosely attached by gravity, drifting along with them through the galaxy at a kind of slow, comfortable remove. This 3rd star is called Proxima Centauri, and Proxima holds a particular kind of quiet significance because it is, by the most careful measurements we have ever made, the single closest star to our own Sun. Proxima Centauri is approximately 4.2 light-years away from Earth. That is a number that can be said in a moment, but understood only gradually, which makes it a perfect number for a night like this. A light-year is the distance that light travels in 1 year, moving at its constant, enormous speed, roughly 9.5 trillion kilometers. and Proxima is 4.2 of those years away. 4.2 years of light travel. If you sent a message to Proxima Centauri tonight, traveling at the speed of light, it would arrive in 4.2 years. A response would take another 4.2 years to return. You would be waiting more than 8 years for a reply. And yet, by the scale of the galaxy, Proxima Centauri is our nearest neighbor, our closest companion in an almost incomprehensible wilderness of space. Distances dwarf any human measurement, with distances dwarf any human measurement with ease. There are still relationships, there are still neighbors, there is still a sense in which things are close, or closer, or closest. And Proxima Centauri, small and dim and quietly glowing, holds that distinction for us. It is the nearest light beyond our own. Human beings have known about Alpha Centauri for a very long time, though they have known it in different ways at different times. The ancient peoples of the southern hemisphere, those who lived where the night sky dipped low enough to show the full sweep of Centaurus, watched this star with the same unhurried attention they gave to all bright things in the sky. In parts of what is now southern Africa, indigenous communities developed detailed knowledge of the southern stars over generations, passing that knowledge forward through story and ritual and careful observation. The stars were not merely decorative to these people. They were navigational. They were calendrical. They told you when the rains might come, when to plant, when to move. A bright star near the southern horizon, reliable and steady, was a useful thing. It was a reference point, an anchor. In ancient Mesopotamia, far to the north, the stars of Centaurus were less visible, sitting low or below the horizon entirely depending on the latitude. But the tradition of careful sky watching was no less serious. The people who built the first cities, who kept the first written records, who developed the first formal systems of astronomy, they were watching the sky with the same fundamental curiosity that much later would lead to telescopes and space probes and the careful measurement of stellar distances. The questions were the same, even if the tools were different. What is that light? How far is it? What does it mean? These are not modern questions. They are ancient ones, asked in every language, from every culture, for as long as human beings have been able to look upward. There is something settling in that continuity. You are resting now, breathing slowly, and somewhere in the long chain of people who looked up before you, there were others doing something similar, lying on the ground, or on a rooftop, or on the deck of a ship, watching the same sky, feeling the same quiet pull of curiosity softened by the late hour. The stars invite this. They are slow enough to permit it. The name Alpha Centauri comes to us through a long chain of transmission. The Greek letters used to name stars were assigned by later European astronomers, working within a tradition that stretched back through Arabic scholarship into classical antiquity. The Alpha designation simply means it is the brightest star in its constellation, a ranking system more than a name. Centaurus itself, the constellation in which these stars sit, takes its name from the centaurs of Greek mythology, those half-human figures associated with the wilder, less domesticated aspects of the natural world. The centaur Chiron, in particular, was associated with wisdom and medicine, with the careful passing down of knowledge from teacher to student. There is something appropriate in that, perhaps. a wise and patient figure standing quietly in the southern sky, holding a star that would one day be understood as our nearest stellar neighbor. For most of recorded history, Alpha Centauri was simply a bright star, beautiful, consistent, useful for navigation, but not understood as a neighbor in any physical sense. The idea that stars were distant suns, that the pinpricks of light in the night sky were objects like our own sun, simply very far away, was understood by some ancient thinkers in a general way, but it was not confirmed with precision until much later. The ancient Greek philosopher Aristarchus suggested something like this, proposing a heliocentric model of the solar system and reasoning that the stars must be enormously distant to appear as small as they did. But his ideas did not become the dominant view. The world was not ready for them, or perhaps the world simply had other things to attend to, and the stars could wait. They always wait. This is one of their most reliable qualities. The stars that make up Alpha Centauri have been shining for a very long time, longer, in fact, than our own sun. Alpha Centauri A and Alpha Centauri B are estimated to be around 5 to 6 billion years old, which makes them somewhat older than the sun's 4.5 billion years. They are not dramatically older. They are not ancient in a way that makes our own sun seem young and fragile. They are simply a little further along, a little more settled, in the quiet way that a slightly older sibling might be more settled. Not wiser necessarily, not more accomplished, simply having had a little more time to exist. There is comfort in the age of stars. They are old in a way that makes human timescales feel very small, and rather than being unsettling, this smallness can feel like a kind of permission. A permission to rest. A permission to let the large things be large, and to occupy, yourself, a very small and comfortable moment within them. You are breathing slowly now. The stars outside, wherever they are visible to you or not, are doing what they have always done. Burning quietly, holding their positions relative to the slow turning of the galaxy, being, without effort, what they are. Proxima Centauri, the smallest and closest of the three, is a red dwarf, a category of star that makes up the majority of all stars in the Milky Way. Red dwarfs burn cooler and dimmer than stars like our sun. They are modest in their output, quiet, long-lived in a way that is almost difficult to comprehend. While a star like the sun will burn for roughly 10 billion years before changing, red dwarfs can burn for trillions of years. Proxima Centauri has barely begun its life by that measure. It has time ahead of it that makes the current age of the universe seem like a brief introduction. And it burns on, steadily, dimly, reliably, at a distance of 4.2 light-years, in a direction that on Earth corresponds roughly to the southern sky. You do not need to find it tonight. It will be there whenever you look. That is the nature of stars at this distance. They are not going anywhere on any time scale that matters to a person resting in a quiet room. They are as fixed as anything in the sky, and this too is a kind of reassurance. In a world of constant small motion and change, the stars hold still. They hold still for you tonight, as they held still for everyone who came before you, and as they will hold still for everyone who comes after. Let your breathing slow a little more if it wants to. There is more to this story, and it will come at its own pace, in its own time, without hurry. The light that reaches your eyes when you look at Alpha Centauri, or any star, is not new. This is one of those quiet facts that, once considered slowly and without urgency, tends to settle into something quite peaceful. The light left its source long before it arrived. In the case of Proxima Centauri, the light you see left that star approximately 4 years and 2 months before it reached you. In cosmic terms, this is a very short journey. In human terms, 4 years is a meaningful stretch of time. Things change in 4 years. Seasons cycle through several times. Children grow noticeably. And yet the light travels all of that distance through the emptiness of interstellar space and arrives at your eye as though it had simply been waiting there, patient and unhurried, for exactly this moment. Sent before you were looking for it, sent before you were looking for it, possibly before you were thinking about it at all. The star simply sent its light outward in all directions, continuously, and some small portion of it happened to reach this particular planet at this particular moment and find its way to you. It did not aim. It did not intend. It simply radiated as stars do, and the universe arranged the rest. This is the nature of starlight, and it has been the nature of starlight for as long as there have been eyes to receive it. Every civilization that ever looked upward was seeing the past. The ancient Egyptians, watching the sky from the flat desert plains along the Nile, were receiving light that had left its source years or decades or centuries before. They did not know this. They could not have known this with the understanding available to them. But it was true nonetheless. The stars were already speaking across time, even before anyone understood the language. The Egyptians had a deep and serious relationship with the sky. Their calendar was organized around stellar observations, the heliacal rising of certain stars, the moment each year when a star first becomes visible on the eastern horizon just before sunrise, after a period of being hidden by the sun's glare, was used to mark the passage of time and the turning of seasons. The star Sirius, for instance, held enormous importance because its annual reappearance in the early morning sky coincided reliably with the flooding of the Nile, that annual renewal of water and soil that sustained Egyptian civilization for thousands of years. The stars were not merely beautiful to these people, they were functional. They were embedded in the practical rhythms of life. Alpha Centauri was less directly central to Egyptian astronomical tradition, partly because of its position in the southern sky and the latitude of Egypt, which placed it low on the horizon and less easily observed than stars further north. But the tradition of careful, unhurried sky watching that the Egyptians embodied was the same tradition that would eventually, in different hands and different places, turn its attention southward and begin to map the stars of Centaurus with precision. Human curiosity about the sky is not bounded by geography. It travels as people travel and accumulates as knowledge accumulates, slowly and over generations. In ancient China, astronomical records were kept with remarkable consistency over very long periods of time. Chinese astronomers documented celestial events, eclipses, comets, the movements of planets, the appearances of new stars, with a patience and thoroughness that has proven invaluable to modern scientists. Some of the oldest reliable astronomical records in the world come from Chinese sources, and they reveal a civilization that understood the sky as a domain worthy of sustained, serious attention. The stars were organized into a system of lunar mansions and asterisms, quite different from the Greek constellations that eventually became dominant in Western astronomy. But the underlying impulse was identical: to name, to track, to understand, to find meaning and utility in the patterns overhead. Alpha Centauri, sitting in the southern reaches of the sky, was at the edge of visibility for Chinese observers in the north of the country, and more easily seen from the south. The star was noted, as bright stars tend to be noted, and incorporated into the broader framework of sky watching that Chinese astronomers maintained. Every culture with a practice of sky observation noted the bright stars. Brightness is conspicuous, even to eyes that are not deliberately searching. A bright point of light in a dark sky draws attention with very little effort on anyone's part. You may find that your own attention, right now, is drifting a little at the edges. This is as it should be. The story does not require sharp focus. It asks only that you remain loosely present, breathing quietly, letting the ideas arrive as they do, gently and without demand. There is no test at the end of this. There is only the night and the slow accumulation of understanding, and the permission to let that understanding dissolve into sleep whenever sleep decides to arrive. The distance to Alpha Centauri was first measured with reasonable precision in the 19th century, which in the long history of human astronomy is quite recent. For most of the time that human beings have been watching stars, the question of how far away they were was essentially unanswerable. Philosophers could reason about it. Mathematicians could propose methods. But the actual measurement required a technique called parallax, a way of detecting the tiny apparent shift in a nearby star's position against the background of more distant stars as the Earth moves around the Sun. This shift is extraordinarily small, even for the nearest stars, and measuring it required instruments and patience, and the kind of careful, repeated observation that was only possible once astronomy had developed the tools to support it. Thomas Henderson, a Scottish astronomer working at the Cape of Good Hope in the early 1830s, made observations of Alpha Centauri that would later be used to calculate the first reliable parallax measurement for the system. He was hesitant about his results. The shift he detected was so small that he worried about the precision of his instruments and the reliability of his data. He delayed publishing. In the meantime, another astronomer, Friedrich Wilhelm Bessel, published parallax measurements for a different star, 61 Cygni, becoming the first to formally announce a stellar distance measurement. Henderson followed shortly after with his Alpha Centauri results, and the two measurements together represented a profound moment in the history of science. The moment when human beings first placed actual numbers on the distance between our Sun and other stars. The result was humbling and magnificent in equal measure. The stars were not merely far away in a vague and general sense. They were far away in a specific, measured, almost incomprehensible sense. Even Alpha Centauri, the nearest of all, was separated from the Sun by a distance that made every previous human journey seem like a step across a room. And yet the measurement itself was made by patient, unhurried people working with the tools available to them, doing what astronomers have always done: watching, recording, calculating, returning again and again to the same piece of sky until the data became clear enough to interpret. Henderson sat at the Cape of Good Hope and pointed his telescope at Alpha Centauri night after night. He watched the same star. He waited. He gathered numbers. He was uncertain, and he sat with his uncertainty. And eventually the picture became clear enough to share. There is a kind of model in that. A willingness to wait for clarity rather than rushing toward a conclusion. The Cape of Good Hope, where Henderson made his observations, sits at the southern tip of Africa, a place that has been inhabited by human communities for a very long time, and that for centuries served as a waypoint for ships navigating between the Atlantic and Indian Oceans. Sailors passing through those waters used the southern stars for navigation, and Alpha Centauri, bright and reliable in the southern sky, was among the stars that helped orient them. The star that Henderson would later measure with a telescope was already known to those sailors as a practical guide, a fixed reference in the turning night sky above a sea that offered very few other landmarks. Navigation by stars is one of the oldest human skills. It requires the same thing that all careful sky watching requires: time, attention, and trust. Trust that the stars will be in the same position tonight as they were last night, and the night before, and 1,000 nights before that. Trust that the patterns overhead are reliable enough to stake a journey on. And that trust, extended over generations, has proven well-founded. The stars are reliable. They are consistent on timescales that matter to human beings. They move slowly enough, across centuries, that a sailor or a shepherd or an astronomer can count on them without fear of being wrong. Proxima Centauri, despite being the nearest star to our sun, is far too dim to see with the naked eye. It is a small, cool red dwarf, and its light, already modest by stellar standards, spreads out across 4 light-years of space and arrives at Earth so faint that it requires a telescope to detect. This means that throughout all of human history, through all the centuries of naked-eye astronomy, through every civilization that mapped the sky and named the stars, and built their calendars and navigations around what they saw, no one saw Proxima Centauri. It was there, burning quietly, closer than any other star, and entirely invisible to unaided human eyes. It was not discovered until 1915 by the Scottish astronomer Robert Innes, working again from South Africa. He noticed that a dim red star in the region of Alpha Centauri appeared to be moving across the background of more distant stars in the same direction and at roughly the same rate as the Alpha Centauri system. This common proper motion suggested it was physically associated with Alpha Centauri, a gravitationally bound companion. Further measurement confirmed that it was even slightly closer to the Sun than Alpha Centauri A and B, earning it the name Proxima from the Latin word for nearest. Proxima Centauri had always been the closest star. It had been the closest star long before there were eyes to see stars, long before the Earth had cooled enough to support life, long before the solar system had fully formed. It sat at its quiet distance, burning its slow red light, and it waited, as stars do, for someone to notice. And now you know. You are resting, and the nearest star beyond our sun is a small, dim, patient red dwarf. And it has been there all along, closer than anything else in the stellar sky, invisible to the naked eye, quietly burning, reliably present. There is no urgency in that fact. It asks nothing of you. It is simply true, and true things, once known, have a way of settling into the background of the mind like furniture in a familiar room. They become part of the landscape, part of what is simply there, steady and unhurried, whenever you happen to think of it. Let your eyes stay closed if they want to. The narration will continue at the same quiet pace, and it will be here whenever you are. There is a quality that belongs to certain kinds of knowledge, a quality of weight without heaviness, of depth without pressure, the kind of understanding that does not demand anything from you, but simply rests alongside you, adding something quiet to the texture of the night. The story of Alpha Centauri has that quality. It is old, and it is large, and it is genuinely remarkable, and yet none of it requires you to do anything at all. You can receive it the way you receive the sound of rain on a window, not as information to be acted upon, but as something that simply accompanies the moment, making it a little richer, a little fuller, without disturbing the underlying stillness. Tonight, we move a little closer to the stars themselves, not physically, not in any way that requires urgency or effort, but in the way of understanding. We follow the line of human curiosity as it developed more precise tools and turned them toward the sky with increasing care. And we find, as we do, that the more carefully human beings looked at Alpha Centauri, the more quietly interesting it became. The two main stars of the Alpha Centauri system, Alpha Centauri A and Alpha Centauri B, are referred to by astronomers as a binary pair. A binary star system is simply two stars in orbit around a shared center of gravity, bound together by mutual gravitational attraction, circling each other on a time scale set by the physics of their masses and their distance apart. There is nothing rare about binary systems. In fact, a significant portion of all star systems in the Milky Way contain two or more stars. Our own Sun, sitting alone in its region of space without a stellar companion, is somewhat unusual in this respect. The universe, it turns out, prefers company. Stars more often than not form in pairs or in small groups, born from the same collapsing cloud of gas and dust, and therefore sharing a common origin, a common age, and a gravitational relationship that will last for billions of years. Alpha Centauri A and B formed together from the same cloud roughly 5 to 6 billion years ago. They have been circling each other ever since, slowly, steadily, their orbital period of approximately 80 years ticking by in silence across the vast stretch of time. 80 years is a long time from a human perspective, and no perspective at all from the perspective of a star. The stars themselves are not aware of the circling, not in any sense that carries meaning. They simply do it the way a stone rolls downhill, the way water finds its level, following the rules of the universe without deliberation, without effort, without any awareness of the elegance of what they are doing. Alpha Centauri A is a star very similar to our own Sun. This similarity is one of the more quietly striking things about the Alpha Centauri system, and it has drawn the attention of astronomers for good reason. Alpha Centauri A is classified as a G-type main sequence star, the same classification as the Sun. It is slightly larger and slightly more luminous than the Sun, burning with a light that is perhaps 10% brighter. But in all the ways that matter to a general understanding, it is a close analog. If you were to look at Alpha Centauri A from a suitable distance, it would appear to you very much as the Sun appears from Earth. A bright, yellow-white star, warm in its color, steady in its output, burning hydrogen in its core with the reliable patience that defines stars of this type. Alpha Centauri B is somewhat smaller and cooler, an orange star, classified as K-type, a little dimmer than the Sun, and a little redder in its light. It is still a substantial star, still radiating enormous amounts of energy, still burning at its core with the same fundamental process that powers all stars. But it is the quieter of the two, the more modest. In a room, if you were imagining these stars as personalities, which is not a scientific exercise but a human one, and perfectly fine to do on a quiet night, Alpha Centauri B might be the one sitting a little further from the center of conversation. Present, warm, meaningful, but less immediately striking than its companion. The two stars move around each other in an elliptical orbit, which means their distance apart is not constant. At their closest approach, they are separated by roughly 11 astronomical units, an astronomical unit being the average distance between the Earth and the Sun. 11 of those distances is roughly the distance between the Sun and Saturn in our own solar system. At their farthest, they move to about 36 astronomical units apart, closer to the distance of our Sun from the inner edge of the Kuiper belt. This means the appearance of the Alpha Centauri system, as seen from any hypothetical planet within it, would change noticeably over the 80-year orbital cycle. There would be times when two stars were closer and brighter together in the sky, and times when they were more separated, one of them fading slightly as the distance between them grew. This is a gentle kind of variability, not dramatic, not alarming, just a slow, decades-long shift in the quality of light, the way seasons shift here on Earth. Gradual enough that any observer watching from year to year might barely notice the change. Significant enough, measured carefully over long periods, to reveal the orbital mechanics clearly. The universe tends to operate at this pace, changes that are real and consequential, but distributed across timescales that make them feel, in any given moment, like stillness. The question of whether planets exist within the Alpha Centauri system has occupied astronomers for many decades. It is a natural question to ask, given the system's proximity and the sun-like nature of Alpha Centauri A in particular. If planets can form around our Sun, and clearly they can, as the 8 planets of our own solar system demonstrate, then perhaps they can form around similar stars in similar circumstances. The search for planets around Alpha Centauri has been ongoing and careful, and the answers, as of the present state of astronomical knowledge, are still unfolding. The complexity of a binary star system creates gravitational dynamics that may constrain where stable planetary orbits can exist, but it does not rule them out entirely. There are regions within and around the Alpha Centauri system where stable orbits are theoretically possible, and where, in principle, a planet could reside. Proxima Centauri, the third and smallest member of the system, has a planet of its own that has been confirmed, a world designated Proxima Centauri b, announced to the scientific community in 2016. This world orbits within what astronomers call the habitable zone of its star, the range of distances at which liquid water could theoretically exist on a planetary surface, given the right conditions. The habitable zone around Proxima Centauri is much closer in than the habitable zone around our Sun, because Proxima itself is much cooler and dimmer. Proxima Centauri b orbits its star in just over 11 days, which places it at a distance of only a few million kilometers, far closer to its star than Mercury is to our Sun. And yet, because Proxima is so cool, this close orbit places the planet within the range of temperatures where water could be liquid. For liquid water on a planetary surface are numerous and specific, and proximity to the right temperature range is only one of them. Proxima Centauri b faces other challenges. The star it orbits is active in certain ways, producing energetic flares that carry radiation outward in periodic bursts. Whether the planet has an atmosphere substantial enough to moderate those flares, to protect its surface, to support the chemistry of water. These are questions that current observations cannot yet answer with certainty. The planet is there. What it is like on its surface remains, for now, a matter of careful hypothesis rather than confirmed knowledge. And there is something comfortable in that, too, in the idea that even our nearest neighbor holds questions we cannot yet answer. It means the story is not finished. It means the patient tradition of sky watching, of careful observation and measurement, of returning again and again to the same region of sky until the picture becomes clearer. That tradition has more work to do. More nights of observation. More instruments turned gently toward the same bright point of light. More accumulated understanding, built the way all understanding is built, slowly and cooperatively, over time. Human beings have been accumulating understanding of the sky for so long that the tradition itself feels like something permanent, something woven into what it means to be human. There is a site in the Lascaux cave complex, in what is now southern France, painted tens of thousands of years ago, where some researchers have suggested that clusters of dots on the walls may represent star groupings, an argument that remains debated, but that points to something important regardless of its specific truth. The impulse to represent the sky, to mark it, to carry its patterns into the spaces where people lived and sheltered, this impulse is ancient. It predates writing. It may predate most of what we call civilization. In the caves, in the dark, by firelight, people looked up at what they had seen the night before and tried to make it permanent, tried to hold on to the pattern, tried to bring something from outside into the inside to make the large and distant feel present and close. This is not so different from what you are doing right now, in a different kind of darkness, in a different kind of shelter, listening to words that carry the sky inside. The impulse is the same. The need is the same. We bring the stars indoors because they comfort us, because they remind us of something older and larger than whatever is pressing on us in the small hours of the night. The Polynesian peoples of the Pacific, who navigated vast stretches of open ocean in outrigger canoes, using the stars, the wind, and the motion of the sea as their instruments, had a relationship with the sky that was simultaneously practical and deeply personal. Star navigation, the art of wayfinding by celestial reference, required a navigator to know the sky the way a person knows the rooms of their own home. Not consciously, not by consultation of charts, but intuitively, in the body, available immediately and without hesitation, even in the dark, even in the motion of a vessel on open water. The great navigators of the Pacific carried the sky inside them. They knew the rising and setting points of hundreds of stars. They knew the star paths, the sequences of stars that rose and set one after another through the night, marking direction and position across thousands of kilometers of open ocean. This kind of knowledge was built over generations. Parents taught children. Masters taught students. The sky was passed down the way language is passed down, not written, but spoken, demonstrated, practiced, internalized. And it worked. The Polynesian expansion across the Pacific, one of the greatest feats of navigation in human history, reaching from Southeast Asia all the way to Hawaii, to Easter Island, to New Zealand, was accomplished with the sky as the primary instrument. The stars guided them. The stars were reliable enough to stake not just a single journey, but the entire expansion of a people across the largest ocean on Earth. Alpha Centauri itself, sitting in the southern sky, was part of the celestial landscape available to Polynesian navigators in the southern portions of their range. A bright, steady star near the southern horizon, useful as a directional reference, incorporated into a system of knowledge that treated the whole sky as a navigational tool. The star did not know it was being used. It simply shone as it always had, sending its light outward in all directions, and some of that light found its way into the eyes of people on small vessels in the middle of an enormous ocean, and those people used it to find their way home. This is what stars do, without intention, without awareness. They provide orientation. They provide a fixed point in a turning world. And on a night like tonight, when the world feels very quiet and the mind is beginning to soften at its edges, there is something in the knowledge of that fixed point, that bright, steady, ancient light, 4 light years away and absolutely reliable, that makes the darkness feel less like an absence and more like a presence that has always been there, a presence that will be there still when the night is over. You can rest now as fully as you like. The stars are holding their positions, as they always have, as they always will, for longer than any of this matters. And that, in its quiet way, is one of the most reassuring things in the universe. There is a particular kind of stillness that comes after a long period of patient attention. Not the stillness of emptiness, but the stillness of saturation. The feeling of having received enough that the mind begins to settle, to organize quietly what it has been given, to let the smaller details soften while the larger shapes remain. This is the kind of stillness that good sleep brings, and it is also, in its own way, the kind of stillness that comes from looking at something very large and very old for a long time. The mind reaches a natural resting point. It stops asking questions for a while and simply holds what it has. If you have reached that point, or something close to it, then what follows can simply be background, a continuation of the same quiet thread, carrying you a little further into the night without requiring anything of you. The story of Alpha Centauri has many layers, and we have touched several of them already. The physical nature of the stars, the history of their measurement, the long human tradition of sky watching that surrounded and preceded our precise understanding of them. Now we move into a different kind of territory, not more urgent, not more demanding, simply a different angle on the same subject, the way a person might shift slightly in a comfortable position without really waking up. We turn, gently, to the question of how far away Alpha Centauri really is. Not in numbers, which we have already visited, but in terms of what that distance means for the possibility of reaching it. This is a question that human beings have been asking with increasing seriousness since the middle of the 20th century, when space travel moved from the realm of imagination into the realm of engineering. And it is a question that, examined slowly and without urgency, reveals something quite profound about the nature of distance, the nature of human ambition, and the nature of patience. The fastest spacecraft ever launched by human beings, as of the current state of space exploration, is the Parker Solar Probe, which has achieved speeds in excess of 600,000 kilometers per hour during its close approaches to the Sun. This is an extraordinary speed by any human standard. It is faster than any vehicle ever built. It is fast enough to travel from the Earth to the Moon in less than 30 minutes. And yet, at that speed, traveling in the direction of Alpha Centauri, the journey would take approximately 6,000 years. 6,000 years, at the fastest speed humanity has ever achieved, to cover the distance to our nearest stellar neighbor. 6,000 years ago, human civilization was in its early stages of complexity. The Sumerians were developing writing. The Egyptians were beginning to unify into a single kingdom along the Nile. Stonehenge was being constructed in stages on the plains of what is now England. The world of 6,000 years ago was recognizably human in many ways. People built, traded, navigated, farmed, buried their dead with care and ritual. But it was also staggeringly different from the world of today. Languages spoken then have vanished entirely. Cities that were centers of power have dissolved back into the earth and been forgotten for millennia before being rediscovered. Whole civilizations have risen and fallen in the time it would take a spacecraft moving at our current maximum speed to reach Alpha Centauri. This is not a cause for despair. It is simply a measurement of the scale of the task, stated plainly and without drama. The distance to Alpha Centauri is not a challenge that human beings are equipped to meet with current technology, and there is no shame in that. The universe does not owe us accessibility. The stars are not waiting impatiently for us to arrive. They are burning at their own pace, on their own schedule, and if it takes humanity many more centuries to develop the means of crossing interstellar distances, the stars will still be there. Proxima Centauri, burning its slow red light, will still be the nearest star. Alpha Centauri A and B will still be circling each other in their 80-year waltz. The distances will not have grown. The stars will not have moved significantly from our perspective. The situation will be very much as it is tonight. There have been serious proposals developed by thoughtful and careful people for how interstellar travel might eventually be approached. One of the most discussed in recent decades is a concept called light sail propulsion. The idea of using powerful lasers aimed from Earth or from space to accelerate an extremely small and lightweight spacecraft by pushing against a sail made of a thin, reflective material. The pressure of light, which is real but very gentle on any substantial object, becomes significant when the object being pushed is small enough and the light source powerful enough. Under such a system, in theory, a tiny probe, perhaps no larger than a postage stamp, carrying miniaturized instruments, might be accelerated to a meaningful fraction of the speed of light. At 20% of the speed of light, such a probe would reach Alpha Centauri in roughly 20 years. This concept, which has attracted funding and serious scientific attention under the name breakthrough starshot, remains in early development. The engineering challenges are considerable, maintaining a laser powerful enough and precise enough over the required distance, building a spacecraft small and resilient enough to survive the acceleration and the interstellar journey, developing instruments miniaturized enough to fit within the constraints of the design, and then receiving the data sent back from 4 light-years away. Each of these represents a frontier of engineering that does not yet have a complete solution. But the concept is not fantasy. It is grounded in real physics. The principles work. The details are what require development, and development takes time. And time, as the stars have always demonstrated, is available in abundance. There is something very human in the breakthrough starshot concept, and in interstellar proposals generally. The same impulse that sent Polynesian navigators out across the Pacific in outrigger canoes, with no certainty of what lay ahead and no guarantee of return, is the same impulse that drives the engineering of tiny laser-propelled probes aimed at the nearest star. The impulse is curiosity combined with reach, the desire not just to know that something exists out there, but to send something of ourselves toward it, to close the distance, even by a little, to make the gesture of approach, even if the approach takes decades or generations or centuries. The Voyager probes, launched by NASA in 1977, carry with them golden records, discs encoded with sounds and images from Earth, chosen to represent the diversity and character of human life on this planet. Music from many cultures, spoken greetings in dozens of languages, the sound of wind and surf and rain, photographs of people and landscapes and scientific diagrams. The probes were launched on trajectories that would carry them out of the solar system entirely, and they have now crossed into interstellar space, the first human-made objects to do so. They are not headed toward Alpha Centauri. Their trajectories take them in different directions, but they are traveling through the same interstellar medium, the same vast emptiness between stars, and they carry their golden records with them into that emptiness as a kind of message, a gesture made not with any realistic expectation of receipt, but with the same instinct that causes people to write letters to the future, to leave things behind for those who come after, to speak into the dark even when no one is immediately listening. The golden records will travel for an enormous length of time before coming anywhere near another star system. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called AC+ 793888. Not Alpha Centauri, not even particularly close to it. But the record will still be traveling. The music will still be encoded on the disk. The greetings in their dozens of languages will still be there, waiting on a medium that, in the vacuum of space, may be extraordinarily well preserved. Whether anyone or anything will ever retrieve that record and play it is a question that cannot be answered. But the gesture itself the act of sending has a meaning that does not depend on the answer. Ancient civilizations left their own kinds of records in the sky, in a sense. The stone alignments at sites like Stonehenge, or the great pyramid complexes of Egypt, or the ancient astronomical observatories found across Central America and South America, were built with attention to celestial alignments, to the rising and setting of the sun at particular times of year, to the movements of the moon, to the positions of certain stars. These structures were not spacecraft. They did not leave the Earth. But they were instruments of communication with the sky, ways of marking a relationship between the ground and the heavens, between the human scale and the cosmic one. They were humanity's way of saying, "We are here, we are watching, we understand that something vast is happening above us, and we have made this mark to show that we are paying attention." The impulse has not changed. It has simply found new forms. A golden record launched on a spacecraft is the same gesture as a stone aligned to the midsummer sunrise. Both say, "We are here. We noticed. We reached toward something larger than ourselves, and we left evidence that we did." Alpha Centauri has been the recipient of this kind of attention in a specific and literal way. In 2016, a brief message was transmitted toward Alpha Centauri from a radio telescope, a collection of binary encoded information, a small modern equivalent of the golden record, aimed precisely at our nearest stellar neighbor. The message left Earth at the speed of light and will arrive at Alpha Centauri in approximately 4 years from the time of transmission. Whether there is anything there to receive, it is unknown. Whether any receiver, if it exists, could interpret it is unknown. But the message was sent, carefully and intentionally, because the act of sending feels important. Because the tradition of reaching towards the sky is so deeply embedded in what human beings do that it continues even when the outcome is uncertain. Even when the waiting time is measured in years, even when the reply, if it ever comes, might arrive generations from now. 4 years for the message to arrive. 4 years for any reply to return. 8 years, minimum, between sending and receiving. And this is for our nearest neighbor. This is the absolute minimum light travel time for any exchange with the nearest star system. In 8 years from today, the earliest possible reply to a message sent tonight would arrive. This is not a frustrating fact. It is simply the physics of the situation, stated as gently as possible. The speed of light is the speed of light. It does not hurry. It does not slow. It simply travels at its constant velocity through the vacuum of space, carrying whatever information it carries, arriving when the geometry of the situation dictates it, will arrive. There is a meditative quality to that constancy. The speed of light is one of the most fundamental constants in the physical universe, a number that appears in the equations that describe space and time and energy and matter, a number that doesn't change depending on the observer or the circumstance. It is the same for everyone. It has been the same since the universe began. Light from Alpha Centauri traveled at that same constant speed when it reached the eyes of the first human beings who looked up at the southern sky, and it travels at that same speed tonight, arriving at any telescope or eye that happens to be pointed in the right direction, carrying its 4-year-old message from the nearest stellar neighbor on time, as always, without variation. there is comfort in constancy. The things that do not change provide a kind of foundation, not exciting, not dramatic, simply reliable. And reliability, in the quiet of the night, is one of the most settling qualities a thing can have. You have been breathing at your own constant pace, in and out, for all of this time. The night has been getting a little deeper, perhaps. The sounds around you, whatever they are, have settled into the background. The story has continued at the same unhurried pace, and it will continue a little further still in the parts that follow, moving through the same quiet territory at the same gentle speed. You do not need to hold any of this tightly. The facts will still be true in the morning, as they were true before tonight. Alpha Centauri will still be there. Proxima will still be the nearest star. The golden records will still be traveling. The message sent in 2016 will still be on its way. The universe will continue to be the size it is, operating at the speed it operates at, holding all of its distances and all of its stars in the same patient arrangement it has maintained for billions of years. And you can rest within all of that. The largeness of it does not press down. It simply surrounds the way the night surrounds, not as a weight, but as a context. A vast, quiet, stable context in which a person breathing slowly in a comfortable place is exactly as significant as they need to be, and exactly as safe. There is a point in the night when the body has largely finished its day. The muscles have released most of what they were holding. The breath has settled into a rhythm that requires no management, no attention, no deliberate effort. The mind, if it is still present in any meaningful sense, is moving more slowly than it was. Thoughts arriving with longer spaces between them, connections forming less urgently, the whole internal conversation becoming quieter and more intermittent. If you are at that point, or moving toward it, then what follows is simply company for the remaining distance. A soft continuation of the same thread, asking nothing, offering only the gentle accumulation of one idea after another, at a pace that matches the pace of a night that is already well underway. We have traveled some distance together through the story of Alpha Centauri. We have looked at the physical nature of the stars, at the long history of human sky watching, at the distances involved, and what they mean for any thought of crossing them. Tonight, in this part of the narration, we move into something slightly different, the inner life of these stars, as science has come to understand it. Not their surfaces or their positions, but their cores. The deep, sustained process that has been occurring inside them for billions of years, that will continue for billions more, and that is, in the most fundamental sense, the reason they shine at all. All stars, including our Sun, and both members of the Alpha Centauri binary pair, shine because of a process called nuclear fusion. This is a word that appears in textbooks and scientific discussions with a certain weight, a certain sense of significance, and that weight is entirely deserved. Nuclear fusion is not a small process dressed in large language. It is genuinely the most energetic, sustained process occurring naturally in the observable universe. And it is happening right now, continuously, inside every star you have ever seen. At the core of a star like Alpha Centauri A, the conditions are extreme by any terrestrial standard. The temperature at the center reaches approximately 15 million degrees Celsius, a number that, stated plainly, simply exceeds the capacity of ordinary imagination to hold. The pressure is similarly beyond ordinary experience, produced by the weight of the entire star pressing inward under its own gravity. Under these conditions of extreme heat and pressure, hydrogen atoms, the simplest and most abundant atoms in the universe, each consisting of a single proton orbited by a single electron, are stripped of their electrons and forced close enough together that the strong nuclear force, which operates only at very short ranges, can take hold. When two hydrogen nuclei are forced close enough together, they fuse. They combine into a new nucleus in a chain of reactions that ultimately produces helium, an atom slightly less massive than the two hydrogen atoms that went into making it. The missing mass does not disappear. It is converted into energy, in accordance with the relationship that Einstein described in his most famous equation. And that energy, released at the core of the star, begins a slow journey outward through the layers of stellar material, eventually reaching the surface and radiating away into space as light and heat. This is starlight. This is what you would see if you looked at Alpha Centauri tonight, the end product of a process that began at the core of that star, traveled outward through its layers over a period that can take thousands of years, emerged from the surface, traveled across 4 light years of interstellar space, and arrived at your eye or your window or the darkness outside it. Every photon of light from Alpha Centauri carries within it the record of a fusion event that may have occurred deep inside that star long before the light even reached the stellar surface. There is a quality of patience in this that mirrors the patience of the night itself. The energy produced at the core of a star like Alpha Centauri A does not rush to the surface. It is absorbed and re-emitted, scattered and redirected by the dense material of the stellar interior, in a process so complex and so slow that the average photon takes an estimated 10,000 to 100,000 years to work its way from the core to the surface. 10,000 years, at minimum, inside the star, bouncing, scattering, being absorbed and re-emitted in new directions, before finally emerging from the surface and beginning the comparatively swift 4-year journey across interstellar space. The light that left Alpha Centauri's surface 4 years ago was energy that was generated at the core of that star, perhaps 100,000 years before it even reached the surface. The photon you might receive tonight has been traveling, in one form or another, for a very long time. This is the kind of fact that arrives quietly and then expands very slowly in the mind. It does not need to be grasped all at once. It can simply be held loosely, the way you might hold a smooth stone, aware of its weight and texture without needing to examine every detail. The light is old, the energy is old. The process that produced it has been running continuously, without interruption, for 5 to 6 billion years inside Alpha Centauri A, and it will continue for billions more. This is not a temporary phenomenon. It is not fragile. It is one of the most durable and reliable processes in the universe. Proxima Centauri, the small red dwarf that is the nearest of the 3 stars, undergoes the same fundamental process, hydrogen fusion in its core, but at a much more modest pace. Red dwarfs are cooler and less massive than sun-like stars, and their interiors mix more thoroughly, cycling material from the core outward and from the outer layers inward in a way that more efficiently distributes hydrogen fuel throughout the star. This makes red dwarfs extraordinarily long-lived, while Alpha Centauri A will exhaust its core hydrogen supply in roughly a few billion more years and eventually expand into a different kind of star. Proxima Centauri is expected to continue fusing hydrogen at its slow, steady pace for trillions of years. The universe itself is currently estimated to be approximately 13.8 billion years old. Proxima Centauri will burn for hundreds of times that age before its fuel runs low. There is something almost incomprehensible in that kind of longevity, and yet it is not alarming or unsettling. It is, if anything, one of the most stabilizing facts available to quiet contemplation. Proxima Centauri is not going anywhere. It is not at risk. It is not approaching any kind of end that needs to concern anyone living today, or anyone who will live for a duration of time that is meaningful by any human standard. It is simply there, burning its patient red light on a timeline so long that it makes the entire history of human civilization seem like a single breath, drawn and released on a cool morning. Human beings have always found ways to map themselves onto large timescales, even when those timescales exceed any individual life. The builders of ancient monuments were doing this in a certain sense, constructing things intended to last beyond any single generation, leaving marks on the landscape that would endure for centuries or millennia. The tradition of oral history, practiced in cultures around the world, carries the same impulse, preserving knowledge and story across generations because the single human lifetime is understood to be only a small portion of a much longer continuum. We are, as a species, aware of our own brevity in a way that seems to be fairly unique. And this awareness has consistently produced the desire to connect with something larger, something that will persist beyond us, that was present before us, that provides a context in which the single human life can feel situated rather than isolated. The stars provide this context with a generosity that requires nothing in return. They do not ask for acknowledgement. They do not need to be watched or named or understood in order to continue their work. They simply persist, burning and shining across timescales that dwarf any human concern, and they make themselves available to any eye that turns upward in any era from any culture as a reference point, a way of situating oneself in time and space, a way of feeling both very small and very much a part of something very large. The ancient Greeks developed a cosmology in which the stars were embedded in crystalline spheres that rotated around the Earth, each sphere carrying its stars at a fixed distance, nested inside one another like the layers of an onion. This model was elegant and internally consistent by the standards of its time, and it served as the dominant framework for understanding the heavens for many centuries in the Western world. It was wrong in its physical details. The stars are not embedded in spheres, and they are not all at the same distance from Earth. But it was right in its fundamental insight that the cosmos is ordered, that the movements of celestial bodies follow patterns, that the universe is not chaos, but something closer to structure. And the emotional quality of that cosmology, the sense of being enclosed within a nested series of spheres, held within the universe like something carefully contained, has its own kind of comfort, even viewed from the far side of the scientific revolution that replaced it. We now know the cosmos to be far more open, far more vast, and far less centered on the Earth than the Greek spheres suggested. The stars are not a backdrop fixed at a uniform distance. They are scattered through three-dimensional space at enormous and varying distances, each one a sun in its own right, some with planetary systems, some without, some burning for billions of years, some for trillions. The universe has no center that we can identify. It has no edge that has been observed. It extends in all directions, as far as our instruments can reach, and then presumably further, into regions we cannot yet see, across distances that make even the distance to Alpha Centauri seem intimate and local. And yet, within all of that vastness, there is still the local. There is still the neighborhood. Alpha Centauri is our neighbor, in the only meaningful sense that word can be applied across interstellar distances. It is the nearest, the closest, the one that sits at the minimum end of the spectrum of stellar remoteness from our own sun. And neighborhoods, even very spread out ones, carry a quality of familiarity. They carry the feeling that comes from knowing what is nearby, from having located oneself in relation to the things closest at hand. You know tonight that the nearest star is 4.2 light-years away. You know that it is a system of 3 stars, 2 of them forming a binary pair, and one of them, small, dim, patient, sitting at the closest distance of all. You know that these stars have been burning for billions of years, and will continue burning for billions or trillions more. You know that light from them, arriving at Earth tonight, began its surface journey thousands of years after the energy that powers it was first released at the stellar core. You know that human beings have been watching these stars in various ways and with various degrees of understanding for as long as human beings have been looking upward at the night sky. This is not a small amount of knowing. It is, in fact, a remarkable accumulation of understanding, built up by centuries of patient observation, careful measurement, mathematical reasoning, instrument making, theory building, and the slow collaborative process by which human knowledge grows from generation to generation. No single person built this understanding. No single civilization developed it. It grew the way a great river grows, from many small streams, each contributing its portion, the whole becoming far larger and more powerful than any individual source. And now it rests in you, lightly and without demand, as you move through the later hours of the night. It does not require anything of you. It does not need to be remembered in its details tomorrow. The stars themselves will hold their positions. The distances will remain as measured. The light will continue to travel at its constant speed, arriving at Earth with the same patient regularity it has always maintained. Nothing about the universe changes because a person rests and lets the knowledge soften from sharp fact into gentle background. There is a quality that long-established things have. Old mountains, old rivers, stars that have been burning since before the Earth existed. A quality of simple, uncomplicated presence. They are not trying to be anything other than what they are. They are not in the process of becoming something else. They are simply themselves, fully and quietly, and their presence in the world is so established, so settled, so far beyond any question of whether they belong, that being near them, even in imagination, even in narration, even in the half-sleeping attention of a late-night listener, carries something of that settledness inward. You belong here, in this quiet moment, as fully as the stars belong in their positions. Nothing about the night requires you to be more alert, more active, more present than you currently are. The story has been telling itself at its own pace, and it will tell a little more in the part that follows. But for now, in this pause, there is only the night and the stars holding their positions beyond whatever ceiling is above you, and the breathing that continues without effort, and the very old light from very old stars moving through the dark in every direction, including yours. You are exactly where you are supposed to be. That is the softest and most reliable truth available at this hour. The night has come a long way, and so have you. Whatever state of wakefulness or sleep you are in right now, whatever degree of awareness remains, it is exactly the right amount. The narration does not require more of you than you have. It asks only that you remain as you are, breathing in the same slow rhythm, letting the words arrive and settle and drift without needing to be caught or held or carefully filed away. This final part of the journey moves at the same pace as all the others, unhurried, observational, following the same quiet thread that began when we first turned our attention outward, toward the nearest star system, toward the small bright point of light that has been shining steadily over this planet for longer than the planet itself has supported life. There is a word that astronomers use, stellar neighborhood, to describe the region of space within a certain distance of our Sun. The stellar neighborhood, loosely defined, encompasses the stars within perhaps 15 or 20 light-years of Earth. Within that neighborhood, there are only a few dozen stars, most of them dim red dwarfs, scattered across an enormous volume of space. Alpha Centauri is the nearest member of this neighborhood. Others include Barnard's star, a red dwarf about 6 light-years away that moves across the background of more distant stars faster than any other known star relative to our Sun. Sirius, the brightest star in the Earth's night sky, sits at about 8.5 light-years, close enough to be part of the local stellar community. Far enough that a journey there would take even longer than a journey to Alpha Centauri. Wolf 359, Lalande 21185, Epsilon Eridani, names that appear in astronomical catalogs and occasionally in the imagination, a small collection of neighboring suns distributed through a region of space that feels, on the scale of the galaxy, remarkably sparse. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, depending on how carefully the counting is done and how the question is framed. These stars are distributed across a disk roughly 100,000 light-years in diameter, with a dense central bulge and spiral arms curling outward through the galactic plane. Our Sun sits in one of those spiral arms, the Orion arm, at a distance of roughly 26,000 light-years from the galactic center. We are not near the center, and we are not at the edge. We are somewhere in the middle distances, in a relatively quiet region of the galaxy, far from the crowded stellar populations near the core, and far from the sparse outskirts where stars become very rare. Within this enormous structure, the stars of our local neighborhood are separated from one another by distances measured in light years. The average distance between stars in our region of the galaxy is several light years. Space between the stars is very nearly empty. Not completely empty, because interstellar space contains gas and dust and particles and radiation, but empty enough that the matter distributed through it is extraordinarily dilute by any standard that applies to ordinary human experience. If you were traveling through interstellar space, you would not encounter anything. You would simply travel through a darkness that is more complete than any darkness on Earth, for years, for decades, for centuries, before arriving at the next point of light. This emptiness is not bleak. It is simply the natural condition of space at the scale between stars. It is the medium through which light travels, through which the Voyager probes are now moving, through which any future interstellar probe would need to pass. It is vast and dark and cold. The temperature of interstellar space, far from any star, is only a few degrees above absolute zero. And it is, in its own way, perfectly suited to what it is. A space between things. A gap that gives the things on either side of it their definition, their separateness, their individuality. Without the emptiness, there would be no neighborhood. There would just be a continuous mass of stellar material, undifferentiated and indistinct. The emptiness is what makes Alpha Centauri Alpha Centauri, a discrete, particular, specific system of stars sitting at a specific distance, with its own character and its own history, related to but separate from our own Sun. The character of Alpha Centauri A, the most sun-like of the three stars, has been studied with increasing precision as astronomical instruments have improved. Its spectrum, the pattern of light emitted at different wavelengths, which acts as a kind of fingerprint for the composition and temperature of a star, reveals a chemical makeup very similar to our Sun's. Hydrogen and helium dominate, as they do in all stars, with smaller amounts of heavier elements distributed through the stellar material. The heavier elements, carbon, oxygen, nitrogen, iron, silicon, and others, were not present in the early universe. They were produced inside earlier generations of stars through the process of stellar nucleosynthesis and distributed into space when those stars ended their lives in various ways, becoming part of the gas clouds from which later stars and planetary systems formed. Alpha Centauri A and our Sun both contain these heavier elements because both formed from gas clouds that had already been enriched by the deaths of earlier stellar generations. In this sense, both stars share a common inheritance, the recycled material of stars that burned and ended before either of them existed. This recycling is one of the most quietly beautiful aspects of stellar astronomy. The atoms in your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood, were produced inside stars that died before the Sun was born. They were distributed into space, incorporated into the gas cloud that collapsed to form the Sun and its planetary system, eventually finding their way into the oceans and atmosphere and crust of the Earth, and then, through the long processes of chemistry and biology, into the living things that have existed on this planet. The atoms are old. They have been many things before they were you. And the atoms in Alpha Centauri A have a similar history, formed in earlier stars, distributed and recollected, now burning at the core of a star 4 light-years away, cycling through the stellar interior, eventually to be returned to space when that star's life ends, to become part of whatever comes next. There is a continuity in this that extends far beyond any individual life or any individual star. Matter moves, energy transforms. The universe recycles its material with a patience and thoroughness that makes any human recycling effort look very brief and very local. And through all of this cycling, through the deaths of stars and the formation of new ones, through the condensation of gas clouds into planetary systems and the eventual dispersal of those systems back into space, the fundamental constants remain constant. The speed of light does not change. The gravitational constant does not change. The rules that govern nuclear fusion in the core of Alpha Centauri A are the same rules that governed nuclear fusion in the stars that died before it, and they will be the same rules that govern nuclear fusion in the stars that form after it. The universe is consistent. It applies its rules everywhere, to everything, across all of time, without exception and without variation. This consistency is, in the deepest sense, what makes knowledge possible. If the rules changed from place to place or from moment to moment, there would be nothing to learn, nothing to understand, nothing to predict or describe. The fact that the spectrum of Alpha Centauri A matches what we would expect from a star of its temperature and composition, the fact that it obeys the same physical laws that govern our own sun, is both an observation and a confirmation of something much larger. The universe is coherent. It is the same universe, operating by the same principles, at Alpha Centauri as it is here, as it is at the edge of the observable cosmos. Whatever understanding we develop here applies there. Whatever we learn about stars in our local neighborhood tells us something true about stars everywhere. Human beings arrived at this understanding gradually through the same patient accumulation of observation and reasoning that characterizes the whole history of science. The idea that the laws of physics are universal, that the same forces and constants apply throughout the cosmos, was not assumed from the beginning. It was tested again and again by comparing observations from different parts of the sky, by measuring the spectra of distant stars and finding them consistent with the same atomic physics that applies in laboratories on Earth, by sending probes to other planets and finding that the same gravitational laws that describe the fall of an apple in an orchard also describe the orbit of a spacecraft around Jupiter. The universe passed every test. It is consistent. It is coherent. It is, in this fundamental sense, knowable. And knowing it, even partially, even imperfectly, even in the gentle and approximate way that comes from listening to a quiet narration in the late hours of the night, is a form of participation in something very large. You are part of the same universe as Alpha Centauri. You are made of the same kinds of atoms, governed by the same physical laws, existing in the same four-dimensional space-time that contains those stars and the emptiness between them and the galaxies beyond them. The distance between you and Proxima Centauri is real and significant, but it is a distance within a shared framework. You are not separate from the cosmos. You are inside it as fully as any star. The southern sky, where Alpha Centauri sits from the perspective of observers in the southern hemisphere, has been a source of navigation and wonder for people across many cultures and many centuries. The Aboriginal Australians, whose connection to the land and sky extends back more than 60,000 years, making their astronomical traditions among the oldest in the world, developed rich and detailed knowledge of the southern sky that was encoded in story, in ceremony, in the intricate mythological frameworks that organized their understanding of the world. The dark patches between the stars, the spaces where the Milky Way's light is blocked by clouds of interstellar dust, were as meaningful to Aboriginal sky watchers as the bright points of light. These dark constellations, as they are sometimes called, were given names and stories and significance. The emu in the sky, a figure traced not by stars but by darkness, stretches across a large portion of the southern Milky Way and was used to mark the seasons, its position in the sky at different times of year corresponding to the availability of emu eggs on the ground below. A practical and elegant use of celestial observation that embedded astronomical knowledge directly into the rhythms of daily life. Alpha Centauri, bright in the southern sky, was part of this celestial landscape, one of the bright reference points in a sky that was read as carefully and as comprehensively as any written text. The sky was not separate from the world for these observers. It was continuous with it. The movements of stars were connected to the movements of animals, to the ripening of plants, to the coming of rain, to the proper time for ceremony and for rest. The cosmos and the community were understood as a single system, and the careful attention paid to the stars was simultaneously an attention to the world directly underfoot. This integration, this sense of the sky as inseparable from the life lived beneath it, is something that modern astronomical practice approaches from a different direction, but does not entirely lose. The scientists who study Alpha Centauri are driven by curiosity that is not merely technical. They want to know if there are planets there because they want to know if there is life there, or the conditions for life, or the chemistry that life requires. They want to know because knowing feels important, not just useful, not just scientifically significant, but important in the way that knowing where you are is important, in the way that understanding your neighborhood is important, in the way that any act of genuine curiosity about the world is important. It connects the person doing the knowing to the thing being known. It makes the distance feel a little less absolute. Proxima Centauri b, the confirmed planet orbiting the nearest star, sits at a distance of 4 light-years and some fraction, the nearest world beyond our own solar system that we know exists. It may be rocky. It may have an atmosphere. It may have water in some form. It may have none of these things. The instruments that could answer these questions with confidence are still being developed, still being designed, still waiting for the engineering and the funding and the decades of patient observation that will eventually produce the data needed to form a clearer picture. The planet will wait. Proxima will wait. The universe is not in a hurry, and neither right now are you. What is certain is that the planet exists, that it orbits a real star at a real distance, that it moves through interstellar space on the same trajectory as its star, carried along by Proxima's proper motion through the galaxy, both of them moving together through the stellar neighborhood, as the entire local group of stars drifts through the Milky Way in its long orbit around the galactic center. Everything is moving, always, at scales both large and small, and yet from the surface of the Earth, on any given night, the stars appear fixed. They hold their positions relative to each other with a steadiness that has made them reliable navigational and calendrical references for all of human history. The motion is real, but it is slow enough, distributed across timescales of thousands and millions of years, that from any human vantage point, the sky looks still. And it is still in the way that matters tonight. The stars are in their places. Alpha Centauri sits where it has always sat, from the perspective of anyone alive right now, and where it will sit for everyone who comes after. The light is traveling, as it always travels, at its constant speed through the interstellar dark. The fusion continues in the cores of all three stars, the bright pair circling each other in their 80-year waltz, the small red dwarf burning its patient light at the closest distance. The planet moves in its 11-day orbit around Proxima, receiving whatever light and heat and radiation its star provides, existing in whatever condition it exists in, holding whatever secrets it holds. And you are here, in a quiet room, at the end of a long narration, breathing slowly. The night has done what nights do. It has deepened and softened, and made the things of the day feel further away, and made the things of the sky feel, somehow, closer. Not because the distances have changed. The distances are exactly what they have always been, but because attention, paid quietly and without urgency to something large and old and steady, has a way of making the largeness feel less like a vastness to be crossed and more like a context to be held within. A stable and ancient and utterly reliable context in which the small, warm fact of a person resting in the dark is not lost but situated, not overwhelmed but contained. Follows on schedules that are not follows, on schedules that are not organized around any human rhythm, but that have proven over billions of years to be extraordinarily dependable. You can release whatever remains of your attention to the evening. You can let the narration soften into background, into texture, into the quiet, acoustic company of words that no longer need to be followed or understood. You can simply be where you are, breathing as you breathe, as the night continues its slow work of carrying you toward morning. Alpha Centauri will be there when you wake. Proxima will be the nearest star. The light will still be traveling. The universe will still be coherent and consistent and governed by the same rules it has always followed. Nothing will have changed in any way that matters to the quiet fact of your rest. The stars asked nothing of you tonight except your presence, and you gave it, and that is entirely enough. That has always been entirely enough. Sleep well. The sky is holding everything in place,